Yeah, so yesterday we talked about alcohols, and that's where we introduced an oxygen atom into our hydrocarbon system, all right? So we had a hydrocarbon, all hydrogens and carbons, and then we took one of the H. There's many ways of thinking about what an alcohol is, all right? You can imagine that we, for an alcohol, took an H off, put an O in its place, and then attached the H to the end of that, all right? Or you can imagine it as inserting the O in between the C and the H. However you want to think of it, it doesn't make any difference. The key is that in the end, we've got this now OH group that's kind of standing out in the structure. So now we want to talk about a related group to it called the ethers. And ethers, again, they're very much related to alcohols, and that's because we have a single oxygen, except instead of it being placed in between a hydrogen and a carbon, we break the chain and we stick the oxygen in between two carbons. So it's as if we've put the oxygen, instead of at the end on an H, we've put it right into the chain. We've built it right into that main chain. And that's what makes an ether. It's got the oxygen that are flanked by two carbon groups, two alkyl groups, all right? So alcohol has oxygen singly bonded. Ether has oxygen singly bonded. Alcohol has oxygen singly bonded to a hydrogen, but the ether has the oxygen singly bonded to two carbons, okay? It's a polar molecule, but it doesn't involve hydrogen bonding because I don't have the oxygen directly bonded to the hydrogen. There is a dipole difference here. Again, we will have a delta negative with some delta positives on the carbons because it's going to draw the electrons that way. But it's not as strong as the H bonding situation, so this simply undergoes dipole-dipole interaction, all right? So its melting point won't be quite as great as the alcohol, but it'll be a little greater than just the alkane, which is totally nonpolar, okay? Ethers have higher melting points than the hydrocarbons, but lower melting points than relative alcohols, okay? And when we say relative, we mean they would have the same carbons and hydrogens. Actually, when we're done with all of our compounds, we're going to find we can actually put titles to all of these for the different intermolecular forces. Only London forces govern this. London forces and dipole-dipole govern this. London forces and H bonding govern these. And so we can put them in the groupings depending on what their intermolecular forces are. Now, this naming method is a little goofy. It's a little strange compared to what we've done up to this point. Up to this point, we've had a definite functional group, and it ends in whatever the ending describes that functional group, -ine, -ine, -all. But for ethers, it's kind of an odd thing. It's kind of strange in which we name it. We don't have a special naming system. We still have the parent chain, but the parent chain is going back to the alkane, all right? Let me go through it. I'll show you an example, and then hopefully the light will go on. So it's like we're going back to alkanes. The second thing is we treat the second alkyl group, the shorter one, and we give it the oxygen, and we give it a name called an alkoxy group. What a great name, all right? So we call it an alkoxy group. It's an alkyl group, carbon, hydrogen, et cetera, with an oxygen, and so it gets the name alkoxy, and I'll show you what I mean in a moment. We replace the YL ending with oxy, and I'll tell you in a moment. Give it a position number on the parent chain. Now this alkoxy group will have the lowest position because it's the functional group. Name the branches that before, place all the branches in alphabetical order. Okay, let's take a look at this one. So here we have an ether, all right? It's got an O in the middle. We want to name this thing. We need to break it into two chunks. We need to break it into the parent and then the shorter one with the oxygen. So here I've got 2, and here I've got 1. So the parent is right here. It's 1, whoops, getting my pen. It's 1, 2. And the group is this one right here. Okay? So the shorter chain gets the oxygen and is named as a branch. And this is not a methyl, but it's a methyl with an oxygen, which makes it methoxy. Isn't that fun? It's a fun name. That makes it a methoxy group. All right? So now we go back to naming our alkanes. We could even have a double bond in there if we wanted. We would just treat that shorter chain with the oxygen as a special branch that has the name methoxy or ethoxy or propoxy. All right? So 1, 2 is ethane, like we started way back at the beginning of this. Ethane. All right? And in the number 1 position, I have methoxy. Now, if I put it in the number 2 position, that's really the same thing, right? So that's one of those cases where I don't need the number because it's really going to get me the same thing. So this is methoxyethane. All right? So let's take a look at this one. Now, they're the same, 3 and 3. So it doesn't matter which one we pick. I'll pick this as the chain, 1, 2, 3. And this then becomes my big giant branch. The base name, propane. And this is a propoxy. Now, this propoxy group could go here, which is what it is, or it could actually come off of this one. That would make it different. So I do need a number. What carbon is it on? It's a 1 propoxy. 1 propoxy, whoops, too much space, propoxy propane. Yes? Because I could take this thing, and I'll just take a different color. I could have it coming off of here, O, C, 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 right? And if I did, and I ignored this thing, then I'd have the propoxy group hanging off of the number 2 carbon, and it would make it 2 propoxy propane. You see what I mean? It would be a different molecule. So I've got a short little branch with an O on it, and then I got this big long chain, right? So that's my branch right there. That's my branch right there. And I have another branch over here. So now I've got a little more complicated. You might think that that's a branch there, but that actually contributes to the long chain, right? So I've got a chain here of 4. And it's on the 2 because it gets the smallest number because it's the functional group. So this is 1, this is 2, this is 3, this is 4. So my main name is what is the N name of this thing? It's a all single bonds, butane. And now I need my branches. This is what do we call this branch? Methoxy. It's a methoxy branch. And what about this one? Chloro. What comes first? Chloro. Chloro is going to go first in the name because of alphabetical. So 3, chloro, 2, methoxy, and then that rolls right into the butane. All right? So it's a little different in that we kind of go back to our ane, ene, ine name, and we put that methoxy group or ethoxy group in general is called alkoxy for any alkyl group on that thing. Where with our alcohols, we had all at the end, and we defined that thing with the all and giving it a number. A little different. So again, drawing is, I always think, the easiest. I work my way backwards. So right there, I'm starting with a hexane, right? So 1, 2, 3, 4, 5, 6. And I've got a 3-bromo. Oops, that's in the number 2 position. Counting errors. Let me use my fingers. 1, 2, 3. There we go. Br. 4,4-dimethyl. CH3. CH3, right? And a 2-propoxy. Oh, goodness, I'm going to run out of room. O. And what you can do here is you can put a regular propyl group. So C3H7, right? Because it's normally 8, take 1 away. So you can put an O and then just C3H7, and then load with H's. H3, H, that goes around the corner there, so there's nothing bonded there. H, full, H2, H3. Okay? So we've got these alkoxy groups that we use just as branches. Okay? So we talked about naming ethers, and let's talk a little bit about isomers. Essentially, because between an alcohol and an ether, we're simply changing the position of the O, then alcohols and ethers are structural isomers of each other. So again, here we have ethanol. The O is at the end here, between the H. Put that O in the chain, and we have, what is this? Methoxymethane. So preparing ethers. Ethers are prepared by putting 2 alcohol molecules together. In the process, a water molecule is eliminated, and the other 2 parts of the alcohols stick together and form an ether. We've already seen examples of this where we've pulled some water out of a molecule, and we're going to do the same in this case. But this reaction is a little different than the other reactions that we've seen where we've removed water. In this reaction, we are sticking together 2 larger molecules to make an even bigger molecule. When you put together 2 larger molecules and kind of weld them together, you can imagine like we're welding things together, building something, we call it a condensation reaction. Now, sometimes students get confused with the term condensation because when you hear the word condensation as new chemistry students, you automatically think of water condensing and forming a liquid, like when you have fog on your mirror in the morning after you take a shower. It condenses and it sticks. That's not what we mean by a condensation reaction, all right? I will explain in a moment why we use this term condensation. No, because you'll make a mistake. You will make a mistake. You are taking water out of it, but you take water out of other reactions as well. They're not condensation reactions. And so then when I ask you to tell me what type of reaction it is, you make a mistake because you think of the water being taken out as opposed to the 2 molecules coming together to make a bigger molecule. Because that's what makes a condensation reaction. And that's why I'm being very deliberate about this discussion. I'll give you a contrast to what isn't a condensation reaction, but we still take water out of it, right? And I'll tell you why that isn't a condensation reaction. The key to the condensation reaction is 2 molecules combine to form a larger product. There it is right there. 2 molecules combine to form a larger product with the elimination of a smaller molecule, but notice it says such as water. It doesn't have to be water when you do a condensation reaction. So let me show you an example of a condensation reaction, and then I'll contrast it with something that isn't a condensation reaction that we've already seen. So here we've got an example where I have this smaller alcohol reacting with this larger alcohol. Methanol and ethanol. Excellent. Ethanol. And here's what happens. Now, it doesn't matter which molecule I remove the OH and which molecule I remove the H. We have to take an H and an OH off of, both of them, and it doesn't matter which one you take the O off of. Now, I'm sure that chemists have done all kinds of investigating to learn which O actually comes off. I don't personally know that information, and I'm not that concerned about it here, really. If you go on and you work on this in great detail, you'll learn which O comes off. So I'm going to just have this H being removed with this OH for no reason. Doesn't matter. Again, I've already mentioned to you, if you want to suck water off of something, what do we use as a catalyst? Yeah, we use concentrated H2SO4. It is a water-loving thing, and it will take water off of something. So what does that do? That frees up an electron here. It frees up an electron here. They form the bond, so we end up with CH3 with the O, and then that bonded to the CH2, and then CH3. And we have our water left, because we still have to have a balanced chemical equation here. Okay, let's name the stuff that we get here. What is then the name of our ether that we have formed? So again, longest chain, there it is there. And there's my short group with the O. What's this going to be called? Yeah, methoxyethane. No one needed because either one is the same thing, right? So methoxyethane. Excellent. Okay? So two bigger molecules come together to become one even larger molecule. Let me contrast that with something like this. CH2, CH3, OH, all right? And we have one molecule all on its own. You put it in that good old concentrated H2SO4. You don't have to write this down. If you are, it's not a big deal. But that's also going to rip off of water, right? It's going to take the OH there and one of the H's there. It's going to turn it into a double bond, CH2, double bond CH2, right? And it's going to give us water, okay? We looked at this yesterday. It's a reaction of an alcohol. This is an elimination reaction. We've taken out a little piece from a bigger molecule. We haven't put together two bigger molecules. So this guy up here is a condensation reaction, and this is an elimination reaction, and we can say that this is a dehydration reaction because we've dehydrated the molecule. We don't call the condensation one a dehydration reaction, even though we've removed water. The purpose of the removal of water was to weld together the two larger molecules to make an even bigger one. So condensation is two coming together to become one, and sometimes a chunk has to come out of it. Okay? All right? Why would we call it condensation? And that's a good question. I'm not 100% sure. But if you make a hydrocarbon into a bigger hydrocarbon, if you make two smaller molecules that might be gases, and you weld them together and make a bigger molecule, right away you've increased the London forces because it's bigger, and it may become a liquid. So it might, the molecule itself might condense. Nothing to do with water, okay? It just happens in this case that we have water as our other product, and then that's confusing for new students because you see condensation and you think water condensing on your mirror, or you know what I mean, that type of thing. But it doesn't have anything to do with the water. It's two bigger ones becoming an even bigger one. Excellent.